What is a motherboard? Understanding the basic components of a computer motherboard. Hello, and welcome back to the Gate and Kernel channel. A computer motherboard is covered with chips, slots, connectors, pins, resistors, capacitors, and many other electronic components. At first, it may look confusing. However, a motherboard is not as mysterious as it appears. You can think of it as the central transportation and communication platform inside a computer. The CPU, memory, graphics card, solid-state drives, hard drives, network devices, audio devices, and other peripherals all use the motherboard to receive power and exchange data. The motherboard does not usually perform most of the computer's calculations. Instead, it provides power delivery, communication pathways, expansion interfaces, and startup rules. Without a motherboard, even powerful components cannot form a complete computer. In this video, we will examine the basic structure of a modern desktop motherboard. The MSI MEG-Z790 Godlike Max will be used as a structural example. By the end, you should be able to identify the purpose of the motherboard's major areas. Chapter 1. Motherboards and development boards are not the same. A computer motherboard connects the CPU, memory, graphics card, storage devices, power supply, and peripheral interfaces into a complete personal computer. A development board is mainly used for learning, experimentation, software development, hardware debugging, embedded system design, and prototyping. Common examples include Arduino boards, STM32 boards, ESP32 boards, Raspberry Pi computers, FPGA development boards, and RISC-V development boards. A development board may include a processor or microcontroller, flash memory, RAM, power regulation, GPIO pins, a clock circuit, a reset circuit, and debugging interfaces. These interfaces may include UART, I2C, SPI, JTAG, and SWD. A desktop motherboard has a different purpose. It supports standardized desktop processors, DIMM memory modules, graphics cards, NVMe drives, SATA drives, USB devices, and expansion cards. Both are printed circuit boards, but their intended use and expansion methods are different. Chapter 2. Why does a motherboard look so complicated? The foundation of a motherboard is a printed circuit board, commonly called a PCB. The visible lines on the surface represent only a small part of the electrical connections. Most power and data traces are hidden inside the board. A modern motherboard contains multiple layers of copper and insulating material. Different layers may carry power, ground, high-speed data, memory signals, clock signals, and lower-speed control signals. The board also contains chips, resistors, capacitors, inductors, sockets, connectors, and protection components. Together, these parts handle power conversion, data transmission, timing, device detection, temperature monitoring, and system control. Modern motherboards are often covered by metal heatsinks. These heatsinks help cool the CPU power system, chipset, and M.2 drives. A motherboard can be divided into the rear I/O area, CPU area, power delivery area, memory area, expansion area, chipset area, and internal connector area. Understanding these regions makes the board much easier to analyze. Chapter 3. The rear I/O area. The rear input and output area appears at the back of the computer after the motherboard is installed in the case. It may include USB Type-A, USB Type-C, Ethernet, audio, HDMI, DisplayPort, Wi-Fi antenna, Thunderbolt, and optical audio connections. Some boards also provide BIOS update and clear CMOS buttons. Keyboards, mice, printers, microphones, speakers, external drives, and other peripherals connect through this area. Motherboard video outputs normally require a processor with integrated graphics. When a dedicated graphics card is installed, the monitor should usually connect directly to the graphics card. Motherboards with built-in Wi-Fi and Bluetooth provide antenna connectors. The antennas should be installed for better signal strength, range, and stability. The number and type of rear ports vary greatly. A high-end board may provide Thunderbolt, many high-speed USB ports, faster networking, and advanced audio. A budget board may provide only the most common interfaces. Chapter 4. The CPU socket and processor area. The CPU is the main computing engine of the system. It executes instructions, performs arithmetic and logic operations, moves data, and controls many system functions. The CPU socket creates the mechanical and electrical connection between the processor and motherboard. Different processor families use different sockets. The socket design, contact arrangement, chipset support, and firmware support must all match. The Z790 platform in our example uses Intel's LGA1700 socket. Depending on the motherboard and BIOS version, it supports selected 12th, 13th, and 14th generation Intel Core processors. LGA means Land Grid Array. The contact pins are located in the motherboard socket, while the processor has flat contact pads on its underside. The processor must be installed in the correct direction. Alignment notches and a small triangle marker help identify the correct orientation. Never force the processor into the socket. Incorrect installation can bend the pins and permanently damage the motherboard. Before buying, verify the socket, chipset, processor support list, required BIOS version, and power requirements. Chapter 5. How CPU power delivery works. Near the CPU socket, you will normally find one or two 8-pin power connectors. They receive 12-volt power from the computer's power supply. However, the processor cores use much lower voltages and require precise regulation. The 12-volt input cannot be sent directly to the processor. The components around the socket form the voltage regulator module, or VRM. A VRM normally includes a PWM controller, power stages or MOSFETs, inductors, capacitors, and protection circuits. It converts the 12-volt input into the lower voltages required by the CPU. It must also supply high current while keeping the voltage stable. When the processor is idle, the power system reduces its output. Under heavy load, the VRM must increase current quickly and minimize voltage fluctuations. High-performance motherboards often use multi-phase power delivery. Multiple phases share the current and heat, reducing stress on individual components. However, phase count alone does not determine quality. Power stage ratings, controller design, cooling, PCB quality, thermal performance, firmware tuning, and real-world testing also matter. Most users only need a motherboard that can provide stable power for the processor they actually use. Chapter 6. The memory slot area. The CPU constantly reads instructions and data. Storage devices are too slow to serve as its immediate workspace. For this reason, computers use RAM to temporarily hold active programs and data. RAM is volatile, so its contents are normally lost when power is removed. Memory slots are usually located to the right of the CPU socket. Standard ATX motherboards often provide 4 DIMM slots, while smaller boards may provide 2. DDR4 and DDR5 memory are not interchangeable. They use different electrical standards, voltages, and notch positions. On a 4-slot board, one memory module is often installed in slot A2. 2 modules are commonly installed in A2 and B2 to enable dual-channel operation. Always confirm the correct configuration in the motherboard manual. Advertised memory speed is not guaranteed in every system. Stability depends on the processor's memory controller, the number and capacity of the modules, memory quality, motherboard routing, BIOS version, timings, and voltage. Memory slots are close to the CPU because the memory bus carries many high-speed parallel signals. Curved or serpentine traces are used for length matching, helping related signals arrive at nearly the same time. Chapter 7. PCI Express and M.2 expansion areas. Below the CPU is the high-speed expansion area. The most visible components are the long PCI Express slots. The top full-length slot is commonly used for a dedicated graphics card. Other slots may support network cards, audio cards, capture cards, storage controllers, accelerator cards, and USB expansion cards. A PCI Express connection is described by its generation and lane count. For example, PCI Express 5.0 by 16 means a 5th-generation interface with 16 lanes. A newer generation provides more bandwidth per lane. More lanes usually provide more total bandwidth. PCI Express 4.0 by 4 provides about 7.9 GB per second of theoretical one-direction payload bandwidth. PCI Express 5.0 by 16 provides about 63 GB per second. These are theoretical interface limits, not guaranteed real-world speeds. The expansion area also contains M.2 slots, commonly used for NVMe solid-state drives. Some M.2 slots connect directly to the CPU. Others connect through the chipset. A direct CPU connection normally provides a shorter path and may reduce latency. A chipset-connected drive can still be very fast, but it shares the chipset link with other devices. PCI Express lanes are limited. Installing an M.2 drive may reduce another slot's speed, disable a SATA port, or change another interface's operating mode. Always check the motherboard's lane sharing table before installing several expansion devices. Chapter 8. The chipset area. Older computers commonly used a north bridge and a south bridge. The north bridge connected the CPU, memory, and high-speed graphics interface. The south bridge handled USB, SATA, audio, and other lower-speed peripherals. Modern processors now include the memory controller and primary PCI Express controller. As a result, the traditional north bridge has largely disappeared. The major support chip near the lower right area of a modern Intel motherboard is called the chipset, or Platform Controller Hub. Its abbreviation is PCH. The chipset acts as an interface expansion center. The CPU reserves its most valuable direct connections for the graphics card and primary NVMe drive. The chipset expands the system with additional USB, SATA, PCI Express, network, audio, storage, and peripheral connections. On the Intel Z790 platform, the chipset communicates with the processor through DMI 4.0. The chipset defines the platform's available resources. The motherboard manufacturer decides how many of those resources become physical ports and slots. This is why two boards using the same chipset can have very different features and prices. Chapter 9. Internal headers and edge connectors. Along the bottom and right edges of the motherboard, you will find many small headers. They connect the board to the case, cooling system, lighting system, and front panel ports. The front audio header connects the case's headphone and microphone ports. A 12-volt 4-pin RGB header normally controls all connected lights as one group. A 5-volt 3-pin RGB header can control individual lights and create moving effects. These two standards use different voltages and pin layouts. They must not be mixed. Fan and pump headers provide power and speed control signals. The CPU cooler fan should normally connect to the CPU fan header. A liquid cooling pump should be connected according to the cooler and motherboard instructions. Internal USB headers connect the front USB ports on the case. Different headers may support USB 2.0, USB 3, or front panel USB Type-C. The front panel header connects the power button, reset button, power light, and drive activity light. Because the pins are small, always follow the motherboard manual. SATA connectors are used for hard drives, 2.5-inch SATA solid-state drives, and optical drives. The large 24-pin connector is the motherboard's primary power input. High-end boards may also provide diagnostic displays and status lights to help identify CPU, memory, graphics, or boot device problems. Chapter 10. Other control chips on the motherboard. A motherboard contains many smaller control chips. The lower left area often contains the audio codec. It converts digital audio into analog signals for headphones and speakers. It also converts microphone input into digital data. Other controllers may include Ethernet, Wi-Fi, Bluetooth, USB, clock, temperature, fan, Super I/O, PCI Express switch, signal redriver, and storage controllers. Some advanced interfaces require separate third-party chips because the chipset cannot provide every function directly. Additional high-speed networking, Thunderbolt, extra USB ports, or specialized storage features may require their own controllers. A motherboard is not controlled by one chip. It is a coordinated system of processors, controllers, power circuits, firmware, sensors, and communication links. Chapter 11. What do ATX, Micro ATX, Mini ATX, and eATX mean? Motherboard sizes are called form factors. Common form factors include ATX, Micro ATX, Mini ATX, and eATX. The form factor determines whether the motherboard fits inside a computer case. A compact case may not support a full-size ATX or eATX motherboard. Size also affects the physical space available for memory slots, PCI Express slots, M.2 drives, power components, headers, storage connectors, and additional controllers. However, a smaller board is not necessarily slower or lower quality. A high-end mini ITX board can still provide strong power delivery, fast networking, premium audio, and high-speed storage. Its main limitation is physical expansion space. Choose the form factor according to the case, expansion cards, cooling system, and storage requirements. Chapter 12. What are BIOS and UEFI? A motherboard requires firmware to initialize and manage the hardware. Traditionally, this firmware was called the BIOS. Modern motherboards normally use UEFI, but many people still use the word BIOS for both the firmware and its settings interface. When the power button is pressed, the computer does not immediately load Windows or Linux. The firmware first initializes and checks the CPU, memory, graphics hardware, storage devices, USB devices, and cooling system. This process is commonly associated with POST, or power on self-test. If the hardware is working, the firmware finds a bootable device and transfers control to the operating system bootloader. The settings interface allows users to configure boot order, fan curves, processor settings, memory settings, storage modes, security, virtualization, integrated devices, and power management. Supported systems may use an XMP memory profile to apply pre-configured memory settings. Incorrect settings can prevent the computer from booting. In that situation, clearing CMOS can restore the default settings. This may involve pressing a button, shorting specified pins, or temporarily removing the coin cell battery. Some boards also provide BIOS flashback, which can update the firmware without entering the operating system. Firmware updates may improve compatibility, fix bugs or security problems, and add support for newer hardware. Never interrupt power during an update, and always follow the manufacturer's instructions. Chapter 13. How to choose the right motherboard. Most users should consider 5 factors. First, CPU compatibility. Check the socket, chipset, processor support list, required BIOS version, and power requirements. Second, form factor. Make sure the board fits inside the case. Third, power delivery and cooling. A low-power processor does not need an extreme VRM, while a high-power processor under sustained workloads may require stronger power delivery and larger heatsinks. Fourth, memory support. Check whether the board uses DDR4 or DDR5, and verify the number of slots, maximum capacity, supported speeds, and recommended configuration. Fifth, expansion and connectivity. Check the number of PCI Express slots, M.2 slots, SATA connectors, USB ports, network ports, wireless features, fan headers, front panel connectors, and display outputs. Do not choose a motherboard only by its chipset name or appearance. 2 boards using the same chipset may have very different power delivery, cooling, ports, and expansion options. The most reliable method is to compare the official specification page and motherboard manual with your actual requirements. Conclusion. A computer motherboard combines power delivery, communication, storage, expansion, control, and firmware into one platform. Once it is divided into functional regions, its structure becomes much easier to understand. The rear I/O area connects external devices. The center contains the CPU socket and power delivery system. The memory slots are located close to the processor. The lower area contains PCI Express and M.2 expansion connections. The chipset expands USB, SATA, PCI Express, and other peripheral resources. The board's edges contain power, fan, lighting, USB, front panel, and audio connectors. BIOS or UEFI firmware initializes the hardware and prepares the system to load an operating system. The motherboard is not usually the fastest computing component, but it is the foundation that allows all other components to work together. The next time you look at a motherboard, you will no longer see a random collection of chips and slots. You will see a complete system made of power, processing, memory, storage, communication, control, and expansion modules. This video uses the MSI MEG-Z790 Godlike Max as a structural example. Different motherboard models may have different layouts, power designs, lane sharing rules, and connector positions. Before installing any hardware, always consult the official manual for the exact motherboard model. If you found this video helpful, please like, subscribe, and share it with anyone who is learning computer hardware. Thank you for watching. If this made hardware easier to understand, Hit that subscribe button for Gate and Kernel. See you in the next episode.